So what I'll do is I'll kind of list the three ways, and then we'll use them in the same situation, just so you can see how they all play out. So the three ways are going to look like this. So one is that torque is Fperp times R, or torque is Frperp, or final one is that torque as a vector is R cross F. Okay, so we're going to look at these three different ways of visualizing it. So the situation that we'll kind of look at is, let's suppose you have this enormous hunk of metal. We'll make it huge. It's like a aircraft carrier component or something. And there's an axis right here, a great big hunk of metal. And this distance right here happens to be 3 meters. And then this distance here is going to be 4 meters. And then what's going to happen is we're going to apply, right at this place, we're going to apply a force that's 8 newtons. So here's an 8 Newton force that's pushing this way. So here's like the axis. I'll even write that down. Here's the axis, and then somebody's pushing on this thing with an 8 Newton force up that way. And so what we're going to do is kind of go one by one and figure out what the torque is provided by this 8 Newton force about that axis. Okay? So the first kind of way of handling it would be, let's look at this one first. So this says torque is Fperp R. And so what we need to do is, well, here's the axis, and here's our distance away from the axis where we've applied the force, right? And you can tell, since that's a 3, 4, well, 5 triangle, so this is going to be 5 meters of this distance. So our effective distance is 5 meters. And so what we need to do, though, is get the effective force, or what's called the Fperp. So we really just need the component of the force that's perpendicular to this thing. So here's our Fperp, right? So we just need to calculate Fperp R. Well, if we're going to do that, we kind of need to know what this angle is, so that we can get the component of F that is along that direction. Right? So one way to see what that angle's got to be is this angle and this angle make 90, right? And so that means that this guy between sort of the horizontal and here is also theta. So those two angles are the same. And so what we could do is, in order to get this particular angle, well, you can see it's just this angle within a 3, 4, 5 triangle, okay? So this Fperp, you could see, would be like 8 cosine of theta. So in this case, if we go to use torque is Fperp R, well, Fperp is going to be 8 cosine theta. And then the R is going to be 5 meters times 5. Well, just continuing along with this, cosine theta, if this is our angle theta, which is also the same as this one, right? Cosine is adjacent over hypotenuse, so cosine theta would be 4 over 5. So cosine theta in this case happens to be 4/5. So we have 8 times 4/5 times 5. Well, so then you get 8 times 4, you get 32. And again, it's a force times the distance, so it's newtons times meters. And then if you remember the direction for this thing, you notice that we're pulling up this way, and here's the axis, so this thing's going to spin around like this. So that's counterclockwise. So you could say that this is 32 newtons times meters, and then you could say it's like out of the page, like by right-hand rule. Okay, so that's your torque calculated using Fperp R. And so again, here's the axis, here's the force. You say, well, really only the component of force that's perpendicular matters. Peel that off, and then multiply by 5. So that's torque is Fperp R. Okay, so that's one way to visualize torque. The other way, though, which, I mean, that wasn't too hard, but the other way, which actually makes this almost comically easy, is this way. If you say torque is Frperp. And so what's meant by this is you say, well, I'm going to use the full 8 Newton force, But if you use the full 8 Newton force, it's not really that this is your effective distance. What your effective distance actually is how far the line of the force is from the axis. So this distance right here, which is Rperp. Well, you can see from the picture that we've built here, this is just 4. Rperp is just 4 meters. Well, so all you got to do then is say, well, I'm going to use the full-blown force, but the effective distance for that force is not actually 5, but it's actually only 4 meters, because the line of the force is 4 meters from the axis. So your Rperp is 4, and straight away you get 32 Newton times meter. Okay, so that's the power of being able to visualize it like this, is it makes it a really fast problem. Just extend the line of the force and see what the distance is. And again, because it's going to go counterclockwise, you could just say that it's out of the page by right-hand rule. Okay, so for me personally, if I'm sort of stuck doing this problem, that one would have popped to mind right away. 8 times 4, bang, it's 32, and you're done with the problem. The final way, which would be overkill for this problem, but there are cases where you won't be able to see it either of these 2 ways, then you're going to go for this way. But full disclosure, I mean, before we get to this one, these 2 ways of visualizing are really going to be your go-to. Like, I use those more than anything in looking at various circumstances with torque. But this is the most kind of formal definition of what torque is. So let's just play around with this to see what's meant here and refresh your memory about cross products. So first, let's write down the 2 vectors. It says R cross F. Well, so we better write down these 2 vectors. So here's the R vector. What this vector is it goes, let's add the little note, this goes from the axis to the place where the force is applied. I'll say to the location of the force. Okay, so let's do that. So the R vector is actually, if you add it to this drawing, this thing here is your R vector, because there's the axis and there's where the force is applied. Well, so that R vector is go over 4 and up 3. So it's over 4, up 3, out of the page 0. And then the F vector is pretty easy to write because it's just 8 going up. So you say force vector then is 0, 8, 0. And what we need to do then is take the cross product of these 2 things. Okay, well, we already know what the answer is supposed to be because we calculated it the other 2 ways, but let's just see how this plays out. So we need to do R cross F. So here we go. So we'll say R cross F is, and then if you remember from pre-calc, you go ijk, I hat, j hat, k hat. Then you put the order matters, so the R vector comes first, 4, 3, 0. F vector comes second, 0, 8, 0. And so we have to evaluate that little determinant. So we'll use the technique where it's called expanding by minors. I know might have been some way that they taught you where you add a couple rows, copy a couple rows over, but or columns. That's a one-trick pony. That's minor league baseball. It only works with like 3x3s. So we're just going to do the way that works all the time for like matrices. So what you do is you start with the I hat component. So you say I hat, cover the row in the column, and then you say 3 times 0 minus 8 times 0. So you kind of go like this. I'll write that down. 3 times 0, whoops, minus 8 times 0. Soon we're not going to keep writing these down, but I'll do it this time because it's been a while. If you remember, you oscillate signs. So we did the I hat component. Now we're on the j hat component. So you have to remember to oscillate signs, minus j hat. And then that's going to be, you cover the row and the column. That's going to be 4 times 0 minus 0 times 0. So again, we still don't have anything. Right? But you know the torque's supposed to come out of the page, so we shouldn't get an I hat or j hat component. But now we are to the k hat component, the last one. So again, you oscillate signs, so we're back to positive. Now you block the row and column under the k hat. So it's 4 times 8 minus 0 times 3. 4 times 8 should sound familiar. Equals 32, positive 32 k hat. Meaning, it's 32 and it's out of the page. Well, why is it out of the page? Because that force is going to make this thing rotate like this. So you notice we got all the same answers. So 32 k hat. So that's the torque. I guess we should put the units out here, newtons times meters. But you notice we get the same 3 answers. Final comment about this, we'll work around on cross products so you can tell before you even start which way it's going to point. A little trick for calculating cross products is you take the first vector and fold it into the second, and that will show you which way the cross product points. So you have the first vector is r hat, and then r vector, excuse me, and fold it into f. So the r vector is this way, the f vector is this way. So r vector, and then just fold it into the f vector, and that comes out of the page. So 3 different ways of thinking about torque. These ones you'll probably use the most, but if you need it, that one's there, and that's the more formal definition.